Hey everyone, this is the third section of two-dimensional kinetics in which we study the impulse momentum method. In this video I'll be covering linear momentum and all of the concepts associated with linear momentum. The governing equation as well, I should probably put that in there. Will be covered. Okay, so the first thing is that we go back to our governing equation, which is the linear momentum is equal to the mass times velocity, which is the principal equation for momentum that simply states that the linear momentum of a particle, or in this case a rigid body, is simply the mass of that body multiplied by the velocity of the body. The sum of the forces acting on a body is the mass multiplied by the acceleration, as covered in section 1 of the topic, or of this topic. That is, the sum of the forces equals mass times acceleration. We notice that in rigid bodies there is no time rate of change in mass. That is, m dot equals m dot naught, which is the initial mass flow, which is 0. Which is a convenient relationship if we consider the linear momentum as the time rate of forces as the time rate of change of linear momentum, like so. If we say that g dot equals the time rate of change of mass multiplied by velocity and use the chain rule, we end up getting mv dot plus m dot u, where u is the relative velocity of the mass flowing out of the rigid body, which is 0, and that's 0. It's covered further in variable mass, which we're not going to look at the moment, but we've said that m dot is equal to m dot naught, which is 0, so this term is 0. So our time rate of change in linear momentum is equal to the mass multiplied by acceleration, where acceleration is the time rate of change in linear momentum. In linear velocity. And that is equivalent to the sum of our forces. The next thing that we will say is that momentum, like a force, can be broken up into directional components. So a direction in the x direction and in the y direction, we can look at those components. So if we've got the time rate of change of linear momentum in the x, we don't need a vector. The time rate of change of linear momentum in the x direction is equal to the sum of the forces in the x direction. Now, if we look at the sum of the forces in the y direction, that's equivalent to the time rate of change of linear momentum in the y direction. Okay, the next thing we're going to consider is that momentum can be changed by a force that acts at a certain time. And that's if we refer back to Newton's first law of motion, which is an object will continue in the same motion unless acted upon by an external force, and we combine that with the second law of motion, which is the sum of the forces is mass times acceleration, we end up getting a time rate of change in linear momentum due to an external force. And that could be represented mathematically like so. So this is our initial linear momentum. And if we add a force between T1 and T2, so there's a force applied for a period of time, if this force is applied like so, we can then see that that's equivalent to our linear momentum G1 plus G2 minus G1, because the force multiplied by time is force is mass times acceleration. If we multiply that by time, then it's mass times velocity, which is linear momentum. So these two terms here are the final velocity, and this is our initial velocity, so we end up getting this is equal to G2, which is the final linear momentum. I'll just pull that up so you can see what I've done there. Okay, that's all for this video. I'm going to cover angular momentum in the next video, and then we're going to look at general plane motion. So we're not going to look at general plane motion. We're going to look at, well, we're just going to look at angular momentum, which is all that's necessary for this next video. Alright, thanks for watching.